All right, so let's pretend we were taking our compounded interest, right? And we assumed that we were doing it for 1%. Um, so actually, well, 100% for 1 year, right? And we just want to see where this number crashes into. So if n was 1, if we compounded it just once a year, you'd get 2, right? We'd double our money, right? If I compounded it twice a year, semi-annually, here I'd have 1 plus a half squared. So that'd be 1.5 squared, which of course is 2.25. So let's do 2.25. All right, so now we're going to start running this number a little higher. So we're going to go 100 times. So if I crunch through that number, I'd get 2.20481. If I did it 1,000 times, I'd get 2.7169. If I did it 10 to the fifth times, I'd get 2.71814. If I did it 10 to the sixth times, 2.71827. If I did it 10 to the seventh times, I get 2.8. And so I'm kind of so as I increase the times I compound this, I'm kind of crashing into a number. Well, what number is that? Well, we call this the natural exponential number, right? This number actually appears a lot more places than finance, but this is where it comes from. So if I took this to its extreme, let's pretend I just want to compound it as much as I can and get as much money as possible, right? If I took it to its extreme, this is the number we come up with. All right, so we call this number E, the natural exponential number, or just the natural number. That's what I know it as, right? And it's 2.7182. And then after that, I'm not too terribly worried about it. Your homework tonight, if you notice it, I just have you write this 5 times. And the reason I have you write it 5 times is that way you can get the numbers somewhat in your head. Most people know pi to 3.14159, and that's good enough, right? That's good for pi. This one you should have in, if you get 2.71, I'd be happy, right? It's just a number. It's a good thing to have in your head. So the natural exponential function looks like this. It's just something a little bit close to 2. Here we're going to graph it real quick. So if we're going to graph this, let's go ahead and graph. I'm going to graph in a different color. Let's just do our fun little color here. We're going to say this is f of, well, it's actually, let's do a little bit matter. F of x equals e to the x. Let's actually just graph in the normal one. Of course, it goes through 1, 0, as they all do. And instead of be at 2, it'd be at 2.7. So about here, I guess. And then we can just kind of graph that in. Now, as you know, I'm going to have you guys do is do transformations on this. If we're going to transform this, here we're just going to move it down 1. So it's going to go through this point. It's going to go, the first point will be at 1.7, so about here. It goes up like this. Here, if I have x equals plus 2, I'm just going to move it to the left 2. So here's my point. I can go ahead and graph that in. All right. And that's that. So let's go ahead and look at something. So where does this natural number pop up at? And so this pops up into a lot of population controls. And so let's actually use something that you'd use exponential functions for. And the natural exponential comes this. And this is, this is extremely convenient at this time of year, right? An infectious disease begins to spread in a small city, population of 10,000. So after 2 days, the number of people affected is the following, right? So it's this many. So it's 10,000, and then you here to actually produce these models take a lot of time, but let's actually look at them real quick. This is a really nice thing to look at, especially with our COVID time, right? I know, tragic, right? I wrote this at least a year and a half ago. At least this set of notes. The notes I'll be writing for you the next couple of weeks will be new. So let's look how infectious disease works. All right, um, so after TP, how many people are infected? So we're going to start with an X amount of people that are infected. I think most people can relate to this nowadays, right? Some of you guys are like super young and like full of life and spunk. And I remember when I was going through, it's like when 9/11 happened, and then you like realize like you're talking to a kid who was born after 9/11. You're like, the world's been different since that, right? And eventually you guys get to a point where you talk to someone who was born after COVID-19. You're like, I'm starting to feel old. Just so you know, just to warn you. All right. So at 0, if we type in 0, hold on. We type in 0 here, how many people are infected? So actually, I'll crunch through this one. So here we'll have 0, so this becomes 1. So I'll have 10,000 divided by 5 plus 2, 4, 5. So it'd be 10,000. Should I write number of zeros? Divided by 150. You crunch through that. You'll get 8 people. Okay? Because 8 times this will give me that. So we start with 8 people infected. After 1 day, if we crunch through the number, we'll get 20 people, or it was actually, the actual number is 20.7. 97. Does it make sense to have this amount of people infected? Kind of. You could say the person's getting infected, he's not infectious yet or whatever. But just for our sakes, we're going to round it to 21. So do me a favor, type in your calculators just so I know you can do it. Find me 2 and then find me 5, and I'll give you the other ones, okay? So this one's 37. Give me 5 and I'll give you the other 2. So if you guys want to split it up, tell me if you plug into 2 into this little beast, what you get and plug in 5. And I'll actually type 1 in. Let me actually type 1 in. If you just replace, yes, conspiracy theories. If you just replace the T, how would we handle the E? Here, let me show you how to type it in. I'll type in 10, and then I'll have you guys type in the other 2. All right, so we're going to go to our calculator, Wolfram Alpha. If you have a standard calculator, that's great. Go ahead and use that. So how would I type this in? I type in 10,000. Then I would put in times, and I'm going to put in the quantity of 5 plus 1, 2, 4, 5. E. Most calculations, you just type in E, and then you can put a caret, and then you're going to put in the quantity of negative 0.97, and then here we'll put in our quantity. Put in times. I don't think I have to. So T in this case will be 10. That's the number I'm crunching. Then I'm going to close the parentheses and close this. And I've done something terribly wrong because it's not multiply, it is divide. Da, 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 da. There we go. The nice thing about this is they call this, well, I call it pretty print because it's what it was called in TI-89. Do you have formula print or whatever you want to call it? That way you can check that what you typed in is what you wanted to. And here we get, of course, 970. Okay. All right. Has anyone typed in the other 2? Yeah, 54 is 2. 2 is 54. So that you typed it in perfectly correct. Yeah, 0.37, just around. We'll round to the nearest human. And the other one is 687. Yep. All right, great. So you guys can type it in. All right, so let's graph this real quick. So how are we going to graph this? So the max we need to graph is 2,000. So we have 1, 2, 3, 4, 5, 6, 7, 8. Let's just make that 2,000. Make 4 then 1,000. So we set our scale. So this will be right here, be the number of infected people. So let's be the number of people. And then we'll have days. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. All right, so here we have at day 0, we're at 8, so that's like negligible on our 1,000 scale. Here we're at 20, so that means this is 100, so like a fifth of this. Here would be half of this. You're at 3, we're a little bit above 100. So about here at 5, we're at 600. So here's, I think I've lost one of the bananas. Each one of these is 200. Oops. That's what the eraser is meant for. Each one of these ticks is 200. Therefore, it'd be a tenth of this. Here at 50, it'd be a fourth of this. And here at 3, it'd be a little over half of this. Here at 5, it'd be each of these is 250. That's fine. So just be a little above here. Can't even split my own marks. This is 500. This is 250. Apparently I need to label them. And then here at 8, we're almost to 10. We're extremely close. And so the graph actually looks like this. Kind of comes in as exponential growth kind of switches over and then levels out. Okay, in fact, let's actually just graph this in Wolfram. So now I already have it up. Hi. All we have to do is say y equals, and then we change this to an x. This is super useless. Let's go to Desmos. Desmos. Oh, hold on before I do that. Copy. All right, go to Desmos. Yep, start graphing. Wow. Yeah, didn't hold it as well as I hoped. Oops. You don't like it? What's your problem? You need a symbol on also. Oh, that goes here. Hold on. Oh, you're being okay. Okay. Yeah. I have one too many still, don't I? Nope. If it doesn't graph, I'll give up in a second. Let's get rid of this because I don't need that. Get rid of this. Now what it's crying about. No. Let me try one more time. Someone's probably giving me hints. Remove the y equals. Sorry. Thank you. Then it tells me what it wants. There we go. Now I gotta zoom way out. Yeah. Um, Gee, this isn't that good a graph either because it's just so small. You just goes pow. Whatever. I'll mess with this and learn this program better. No, no. I'll mess with it later. I won't make you guys watch it. The curve flattens after a fifth of population. Yeah, so about a fifth of population it kind of flattens out. So this could mean a lot of things. Stability. A fifth of the people were already immune to it. It doesn't hit everybody. So it's just something to get used to. This is how to work with exponential things. All right, so let's do continuously compounded interest. Okay, so if we're going to do continuously compounded interest, what the real world uses, I need to throw this away. Apparently, that's a whole bunch of hogwash. Just throw this away. I'll go edit my notes. And I believe that for over a year. Oh, it's good to be educated. So now let's get to here. So for continuously compounded interest, let's pretend we actually compounded this continuously. This is our new formula because the 1 over 1 plus 1 over n z, well, this becomes, this ends up becoming e, and then the r actually comes out somehow. And I won't get into the actual math of how to do that, but so we'll just crunch through this number. So here's our new thing. So we have 30,000, and then we're gonna, oops. So on my amount after 4 years, so I'll plug in 4, we 30,000 e to the 0.07. And multiply that by 4. And we just crunch through that and we get 3963. And so that's all you need to do to calculate continuous interest. I think I give you one problem to do on that. All right, so that's all there is for 4.2. It really just introduces the concept of E. We use this in compound interest. We use this for graphing. This number comes up a lot in other places, in physics and everything. It's just one of those, like pi, it just shows up everywhere.